What's up, Huskies? Let's talk about growing number 6, where we actually begin to learn about exponential decay. So our objective today is I can find decay rate and decay factor and use them to write explicit equations. We started off the self-starting class, if you were there, talking about a pair of jeans that's regularly $50 and they are on sale for 15% off. What is the sale price? So I just want to talk about two different ways we could do this problem. The first way might be the way most of you think about this, is that the jeans are $50 regularly and 15% of that would be $7.50. That's how much I'm going to save. And so then the sale price of the jeans is 50 minus $7.50, which is $42.50. That's the sale price of the jeans. Okay, the way that I would like you to think about this problem instead is kind of what we talked about when we were learning about the sales tax, is that we are not paying 100% of the jeans. We get to save 15%. And so what we're actually paying for the jeans is going to be 85% of the regular price. So that's going to be $50 times 0.85. And the calculator just helps me jump right to the $42.50. I didn't have to do that extra subtracting step because I already subtracted in this step. So this whole concept of I'm saving 15%, so I'm going to keep 85%, that's kind of what we're talking about with decay. So then we had a worksheet with a little Dogbert comic on the top, and it talks about how the Dogbert dog is going to take 10% of an investment every year. And that's his fee. And the kind of idiot customer says, oh, sounds good to me. And so, well, if the fee is 10%, then how much is the customer keeping? He's keeping 90%. And so out of that $100,000 investment, we're going to start with $100,000, that's a comma, we're going to keep 90% of it. And so after 1 year, there's only $90,000 left in his account. Now, don't think that this is going to be some kind of arithmetic equation where you just subtract $10,000 every time, because you think about it, now the dog is taking 10% of $90,000, which isn't going to be $10,000 anymore. In fact, it's only $9,000. So after 2 years, what is left in the account is 90% of $90,000, which is $81,000. And then the next time, it's going to be 81,000, comma again, times 0.90, and that ends up being, I think, $72,900. So it's not subtracting $10,000 every year. The 10% fee is getting smaller and smaller because the amount of money in the account is getting smaller and smaller. So I just did this little comparison here. On the left is what it would look like if it was linear. If it was linear, then you would be subtracting $10,000 every year. And so in the beginning, you would have $100,000, and then after 1 year, you'd have 90. After 2 years, you'd have 80,000, which is 90,000 minus 10,000, and so on. But that's not what's going on. Truly, we are talking about an exponential function because we're multiplying by 0.9 every time. So this brings us to this little summary here. The next 4 pages are going to be some notes that you might want to put in your composition notebook or write it somewhere on your classwork so you can have it to help you with the rest of the homework, because this is kind of the big idea for the day. So we've been talking about exponential growth, and that's when we talked about the rabbits and the mold, that it starts small and before long it's huge. That growth pattern right there, that curvy line where the rabbits just exploded after 6 years, right? Remember that? That's exponential growth, and that's when the growth factor that we're multiplying every time is greater than 1, and the rate is a positive number. So then we're talking about exponential decay today, and that would be where we started large, like the $100,000, but we're losing money every year, and we're eventually going to get almost down to 0. And that would be if your growth factor, which we're actually going to call the decay factor, is less than 1, and the rate is negative. In other words, we're losing 10%, or we're, that kind of thing, where it might not specifically say negative 15, but if something's on sale and it's 15% off, that means that it's a negative 15%. We're losing 15%. Okay, I want to take this second right here and talk about one of my favorite math words, and it is spelled kind of funny, and it sounds like you're swearing. It's asymptote. An asymptote is just a line, and something that might help you kind of see which line I'm talking about is to think of the asymptote kind of like a runway. So if I'm talking about an airplane, maybe this orange line is the path of the airplane. It's taking off on the runway, and then it takes off. So the belly of the plane will never actually touch the runway, hopefully, because that means it crashed. The wheels will keep it off of the runway. So it's getting closer and closer to that runway, but never actually touching. And here it took off. And then on the decay, the airplane is landing. It's getting closer and closer and closer to that runway, but never actually touching it. That line that I'm approaching right there is called the asymptote. So in this case, it would be this line right here, where y equals 0. That's the asymptote for this graph. So think about the genes, or even the $100,000 investment. With the investment, is that stupid guy ever going to have no money at all in his account? Is he ever going to have 0? Will he lose every penny? The answer is no. It'll get very close to 0. He'll lose almost all his money, but he'll never lose every penny of it because we're still keeping 90% every year. Okay, how do you turn decay rate into decay factor? Well, remember that the rate is always the percent. So first of all, you need to realize that this is decay and write your rate as a negative percent. So for example, the problem says, hey, this is 30% off. Then you would think of that as negative 30%, something like that. You're going to add 100%, so you would add 100% to your negative rate. Right, for this example, it would give us 70%. Then we're going to divide by 100 to represent our percent as a decimal, and that would become our factor, our decay factor this time. Remember, we're not talking about growth anymore, we're talking about decay, and this should not be a percent. You have turned your percent into a decimal. And it is a decimal less than 1. If we're looking at our factor that we just did right here, 0.7 is less than 1. The fact that it's less than 1 is what makes it decay. That's what's going to make it get smaller and smaller and smaller every time, instead of larger and larger like the rabbits or the mold. How about going the other direction? If you've been given the decay factor and you want to turn that into decay rate, you have to first multiply by 100 to turn it into a percent and then subtract 100%. We're looking for a negative percent when we do this. So it's time for an example. What about if I gave you an equation and it starts like this, 246 times 1.78 to the x power? Well, before when we did that, we looked at that and it was growth, and you would take the 1.78 and you would turn it into a percent and say it was 178%, and then you would have subtracted 100% and you would have got 78% is your growth rate. And that is totally true. And notice, none of my directions have changed. To turn any kind of a factor into a rate, the directions are exactly the same. So now let's look at one that's going to end up being decay. So we'll start off the same way, 246 times 0.78, like that, to the x power. First thing I notice is that the factor is less than 1, so I should be thinking this is decay. But it's the same process that we went through before. 0.78 is the same as 78%. And then if I was going to subtract 100% from that, now you got to think of it as kind of like 100% minus 78%, or heck, just type it on your calculator, and you're going to get negative 22%. Am I right? 100 minus 78? Yeah, should be negative 22%. And that's exactly what our decay rate is. Should be a negative percent. Oh, I'm losing 22% every time for that example. Okay, another summary. If the factor is greater than 1, it's going to grow. If the factor is less than 1, it is decay. So again, you might want to copy that down in your notes. Pause the video right now. Okay, welcome back. All right, I got 3 examples down here at the bottom of the page, and I'm just asking you to decide, is this decay or is it growth? And the thing you look at is what's in the parentheses, the pattern, the thing you're multiplying by, the factor. If it is greater than 1, it is growth. And so this very first one is greater than 1. 1.01 is slightly larger than 1. So this represents growth. How about example number 2? The thing in the parentheses, 0.3, that's less than 1. So this must be decay. You can figure this out, right? It's not that bad. How about this one, 0.99? Is that greater than 1? Nah, it's a little bit less than 1. So this must be decay. Awesome. On the homework, we are talking about Letitia and her licorice. And she is going to cut the licorice, and we have 2 plans here. So the first plan that Letitia does is going to be, well, let's just see. They'll be different. So 1A, how many cuts? At the very beginning, I know the table on your homework does not have 0. I added that because I thought it made a little bit more sense. So if she hasn't cut the licorice at all, how much does she have? Well, she still has 24 inches. Now, Letitia is going to cut the licorice in half and give her friend half of what she has left. So half of 24 is 12. She gets to keep 12 inches. Then after 2 cuts, she only has 6 inches left because she's cut her 12 inches of licorice in half and given half away. Now she cuts the 6 in half and she only has 3 inches left. And so on and so on. And she keeps finding or keeping half of her licorice. Now, think about this. If she keeps just cutting it in half and giving half away, is she ever going to run out of licorice completely? The answer to that is no. She'll have the tiniest little molecule of licorice left, and then she'll cut that in half, but she'll still have some licorice. So this reminds me of exponential decay. I hope it reminds you of decay also. And we would have an asymptote of y equals 0 again, because although it's getting very close to no licorice left, it's never going to quite get to 0. Now let's see, you can graph it, and it should make a sort of a curved, sort of slanted downward thing. I'm not going to do that right here, but I'm going to talk about the plan in C. Now instead of giving away half of the licorice, this time Letitia is just going to give a friend 4 inches of licorice. So before she starts cutting it at all, she still has 24 inches of licorice. Now she cuts off 4 inches and gives it away. How much does she have left? She has 20 inches left. Then she cuts off another 4 inches. She has 16 and 12 and 8 and 4. Uh-oh, she ends up with no licorice left after 6 cuts. So in other words, this one is different than the exponential decay because we did get right to 0. She completely ran out. And did you notice the pattern here? The pattern here is not multiplying. We are subtracting 4 every time. What could we call that? Well, we call that being linear. So plan C is linear because it's just subtracting 4 every time, and that reminds me of arithmetic, and arithmetic is like being linear. But the first one, that was exponential decay because it was being multiplied every time by 1/2. And 1/2 is smaller than 1, so my factor is less than 1, so it's decay. All right, on number 2, we're going back to Chen. And this time he decides, hey, this paper is too small. And so I'm going to start with a bigger paper, and when I cut it to make my ballots, I'm going to have bigger ballots. So this time he starts with paper that is 64 square inches. And he cuts it once in half, and there are 32 square inches of paper. Then he cuts it in half again, and there are 16 square inches of paper. Cut it in half again, 8 inches of paper, 4, 2, etc., etc. You get the idea. Okay, now I left some space at the top of this because on number 10, Number 10 says, let me see if I went on. Oh, here's number 10. 10 says he wants to be able to make 12 cuts before his ballots have an inch of paper or less. So looking back at this, I didn't quite make my table long enough here, but if we cut it one more time, 6 times, his ballots would be exactly 1 square inch. For number 2, right? We're all on number 2. After 6 cuts, he has exactly 1 square inch of paper for a ballot. That's a tiny little paper. And so on number 10, he's saying that he wants to be able to cut it 12 times before he gets ballots that small. How large does he need to start with? Well, there's a couple of things you could do here. You could maybe write an explicit equation and do some guessing and checking with a few numbers. I think it might be easier to kind of roll this back a little bit. So that's what I'm going to do here. That's why I left some room at this table. I'm saying that I would like to be able to cut this thing 12 times before I get to 1 inch. So right now I have on the area of 1 inch right there that's my 6th cut right now. But, well, what if I said that was going to be my 12th cut? This would be my 11th, 10th, 9th, 8, 7, 6, 5, 4, 3. And you can see that by rolling this table backwards a few times, I could figure out how big my paper needs to be to start with. So I know in this situation it doesn't really make sense to talk about the -1 cut, but if we roll this table back, how big will the paper be? It will be 128, because I'm timesing by 2 now going backwards, and then would be 256, which for number 2 problem would be like the -2 cut, but on number 10 we're just trying to figure out where would we end up. So we're kind of working backwards recursively, and if you keep going like that, you've got 256 times 2, and then you've got times by 2 again, times by 2 again. How many times do you need to keep going? You end up with paper that is 4,096 square inches, because we had to roll that back 3, 2, 1 more time. 3, 2, 1, yeah. So check and make sure I did my math right. Is 256 times 2 times 2 times 2, 4,096 square inches. Okay, I hope that's enough information to help you out on number 10. I just want to review quickly one more time on number 12. It says it says y equals 0.8 times 2 to the first 2.1 to the x power. And the question is just, hey, is this decay or growth? Remember what you're looking for in the parentheses. That factor is larger than 1, and so it must be growth. If the number is less than 1, it would be decay. All right, I hope that helps you fill out the rest of your homework well enough. Good luck, and let me know if you have any questions.